Exponential functions can model many processes, such as the unrestricted growth of bacteria populations in scientific studies or the growth of money invested for goals such as education. The Federal Reserve Board chairman has stated that consumers need more financial knowledge to navigate today's increasingly complex financial services marketplace. Financial concepts such as compound interest, future value, cash flow, and amortization may seem confusing or even intimidating. The good news is that with an understanding of the algebra of exponential functions, and with the help of a graphing calculator, you can get a head start at becoming money savvy. In real-world applications, the variable x most often represents time, so the letter t is often used in lieu of x. Also, we usually examine y for positive values of x. The exponential functions used to model financial and scientific applications take on slightly different forms. Instead of the simple y equals b to the x power or y equals b to the t power, we will encounter the general form y equals a times b to the t, where a represents the initial amount of some quantity at time 0. We're ready for our exploration. Suppose a relative or a friend has just had a baby. Family and friends get together and decide that instead of buying gifts, they will start an education fund for the baby. Suppose they raise $1,000 and invest it in an interest rate of 5% for 15 years. The initial investment is called the principal. 5% is the interest rate, and 15 years is the length or the life of the investment. How much money will accumulate in the account over 15 years? We'll begin by deriving the equation for annual interest, which means the interest is compounded once a year. When t equals 0, we begin with the initial principal p. At the end of 1 year, the amount of money y will be the principal p plus the interest I gained on the principal. The interest gained is r times p, where r is the interest rate expressed as a decimal. Factoring out p yields p times quantity 1 plus r. The implied exponent of 1 indicates the amount of money after t equals 1 year. Each year, the previous amount is multiplied by quantity 1 plus r. So, after t years, the amount of money y in the account would be y equals p times quantity 1 plus r to the t power. This is an exponential function of the variable t with base 1 plus r. Let's use this formula for annually compounded interest to solve our problem. Substituting 1,000 for p and 0.05 for r in the general equation gives y equals 1,000 times quantity 1 plus 0.05 to the t power, or 1,000 times 1.05 to the t. We recognize this form, y equals a times b to the t, where a is 1,000, b is 1.05, and t is the time variable. Let's graph this function with our graphing calculator. Start by pressing Mode. Place the cursor on number 2 of line 2 and press Enter. The highlighted 2 means that all decimals will be rounded to the nearest hundredth. Press Y equals, clear all functions, and when you're done, scroll back up to Y1. Enter 1,000 times 1.05 to the t power. That's 1,000 followed by the left parenthesis, then the decimal 1.05, followed by the right parenthesis, then the power key, and finally the x variable key. In function mode, this calculator uses x for the independent variable. So here x stands for time t. Press Window. Let X range from 0 to 25 years. Leave X scale at 1. Let Y range from 0 to $3,000. Change Y scale to 150. Leave X res at 1. Press Graph. This looks like a slowly increasing function for two reasons. The base, 1.05, is very close to 1, and the selected Y range is much larger than the X range. Press Trace followed by the right arrow to find the point where X equals 15. You'll see that after 15 years, the money more than doubles. If $1,000 invested at 5% more than doubles in 15 years, that means that the interest earned is over $1,000. Similarly, $5,000 would grow to about $10,000 in 15 years, earning over $5,000 in interest. Change the interest rate from 5 to 10% and see what happens. In reality, two facts complicate our equation a bit. The interest is usually compounded more often than annually, say, once a month, and monthly payments are usually involved. But the graphing calculator has a wonderful feature called Time Value Money, or TVM Solver, that can help us solve many financial applications, including this new one. Suppose the family invests $100 in a mutual fund whose interest rate has averaged 11% over its 30-year history. They also plan to contribute $100 each month until the child turns 18. Let's use TVM Solver to explore this. Press the application key called Apps right under the X key. Press 1 for Finance and 1 again for TVM Solver. Since n is the number of months, enter 12 times 18 for 18 years. Press Enter. The calculator works out the product. Here, I is the interest rate as a percent, not a decimal, so enter 11 for the expected rate of return. Then press Enter. PV is the present value, or the initial principal of $100. But since this is cash outflow, it leaves the family's pocket. Enter -100, then press Enter. The next variable is payment. Enter -100 for the monthly contribution, since this also is cash outflow. Then press Enter. Next comes the future value of the investment. Enter 0 for now, then press Enter. We'll come back to solve for this. Set the next two variables to 12 for the number of monthly payments and compounding periods. Finally, select End by pressing Enter to indicate that payments are due at the end of each period. To solve for the future value after 18 years, move the cursor to FV. Then, press the green alpha key followed by the Enter key to access Solve. The result is about $68,111. So, with the principal of $100, combined with monthly payments of $100, which comes to about $3.30 a day, the education fund would grow to over $68,000 in 18 years. Since the total cash outflow over 18 years would be $21,700, this represents more than a threefold return on the investment. In fact, you can solve for any variable, as we solved for FV, by pressing alpha followed by Enter, which gives you Solve. Suppose you're in the market for a used car. Say, for example, this one. A 2001 for $15,000. That must be a loaded one. Let's try working out a car loan that suits your budget using the TVM Solver, okay? Set the future value to 0 to indicate it's paid off. Suppose the interest rate on the unpaid balance is 7%, and the loan is for 60 months or 5 years. Solve for payment and see if the monthly payment is affordable. Now let's hear from a banker for a professional's viewpoint on exponential growth and decay when it comes to personal finances.
My name is Andrew Cervantes. I am a client manager in Premier Banking and Investments with Bank of America, and I advise my clients and recommend the right products and financial solutions to help them meet their financial goals. Math is important in my job as a banker because I'm always demonstrating to a customer or client how saving and investing in the compounding effect of interest over time will impact their deposits with us, or through investments, the time value of money over a period of time. There are various kinds of accounts that will help people achieve various goals. If someone has a short-term goal of, let's say, buying a laptop computer in a year, they want to save for that, I might recommend a savings plan through a regular savings account, or maybe a CD, a time deposit, that will accrue interest over time to achieve their goal. Or if it's something longer term, like saving for college, then we would typically recommend a different type of account that would utilize mutual funds or stocks or bonds or a mixture of to reach that goal. You can figure out how many years it will take for you to double your investment at a given rate of return. An example would be a $1,000 investment at 10% would take 7.2 years for that to turn to $2,000, and then another 7.2 to turn to $4,000, and so on. And so that is it's a quick formula to illustrate the power of compound interest.
That confirms that exponential functions come into play in the real world of finance. And, as we've learned, the graphing calculator's TVM solver is a powerful tool. Before graphing calculators, we had to use logarithms to answer how long questions, such as how long will it take my investment to reach $100,000? That's because logarithmic functions are inverse functions of exponential functions. With exponential functions, we set a time and solve for the money. With logarithmic functions, we set a financial goal, i.e. money, and solve for the time. I hope you'll practice using the TVM solver to help yourself and others become fiscally fit for the future. Now it's time for our final application.